Hello everyone, it's Chemicator. Welcome to the first episode of the Synthesis Studio series. In these types of videos, I'm gonna put more focus on the basics of organic synthesis by creating a target step by step, breaking down all the mechanisms, reagents used, and of course, stereochemistry. Super useful if you are preparing for exams. So it's not just about the synthesis of a target. Along the way, you will learn a lot about different strategies and concepts in organic chemistry to help you level up your synthetic skills. Here the focus is on the tutorial style breakdown of the synthesis fundamentals. If you are looking for more challenging targets and brand new strategies, check out my total synthesis playlist to feed your curiosity. Let's get started with the synthesis of Minfiensine. The core skeleton is composed of tryptamine and monoterpene units, which are also found in other related alkaloids such as acadamine and vincurin. Before exploring the synthesis pathway, we should understand the connections between atoms and bonds. So let's take a closer look at the 3D model of our target. Minfiensine consists of a pentacyclic core. This is the indolin moiety, which is joined to a 6-membered ring. As you can see, there are two substitutions attached to this ring. Now let's see the molecule from the back view. There is a 5-membered ring attached to the indole core, which is a little tricky to see clearly in a 2D drawing. Additionally, there is another 6-membered ring visible from the bottom of the molecule, sharing one carbon atom in common with the indole core. In 2005, Professor Overman's group presented the first enantioselective approach for creating this target. The key chemistry of this strategy is based on an enantioselective Heck reaction. So let's review the mechanism of the Heck reaction step by step. The goal of the Heck reaction is to couple an alkene with an organic halide or triflate to form a new alkene. The first step of the reaction is called oxidative addition, in which the metal inserts into the single bond. It's called oxidative because the formal oxidation state of the transition metal increases by 2, and it's an addition because the metal gains 2 new ligands. The resulting palladium R sigma bond in such complexes is very reactive, especially toward carbon-carbon pi bonds, so it coordinates to the alkene. After that, the complex undergoes migratory insertion. In this process, the R group on the palladium migrates to the one terminal of the carbon-carbon double bond, and at the same time the pi bond forms a sigma bond with the metal from its outer terminal. The next step is beta hydride elimination, in which the beta hydrogen relative to the metal center migrates to the palladium, and the newly formed alkene is released from the complex. Notice that the palladium complex is now in the +2 oxidation state, so it must be converted back to the 0 oxidation state to start another catalytic cycle. For this, a base is required to regenerate the palladium 0 catalyst. This step is called reductive elimination. But what about the enantioselective version of the Heck reaction? It is possible to induce chirality at the quaternary carbon atom of the product by using chiral ligands in the palladium complex. A variety of chiral phosphine ligands are frequently used for asymmetric Heck reactions. During the synthetic pathway, you will get more familiar with how enantioselective induction works. So let's continue. The synthesis begins with the formation of an enamine from morpholin and 1,2-cyclohexadione. Notice that the dione compound exists almost entirely in its enolic form, so morpholin attacks one of the carbonyl groups. The next step is transamination. In acidic media, the nitrogen atom in morpholin donates its non-bonding electrons to the adjacent carbon to assist in the protonation of the double bond. Next, 2-siloxyaniline attacks the carbon atom of the iminium ion, and the bonding electrons move back to the nitrogen atom. At this stage, a proton is eliminated from the molecule to form a double bond, which kicks off the morpholin. This reaction is called transamination because two amine groups exchange their positions during the reaction. In the next step, This intermediate reacts with sodium hexamethyl disilazide as a base. But which is the most acidic proton in this compound? There is one acidic proton in the alpha position of the carbonyl group, and another is attached to the nitrogen atom, which is actually more acidic than the other. So we face a chemoselective reaction in which the base abstracts a proton only from the nitrogen atom. Choosing the right base is also important. The advantage of NaHMDS compared to other bases like sodium hydroxide is its non-nucleophilic property. Due to its larger size compared to NaOH, it can't attack sensitive groups such as carbonyls. After reacting with NaHMDS, the nitrogen atom attacks methyl chloroformate to form the carbamate. The goal of this reaction is to selectively protect the nitrogen atom. After protection, NaHMDS is used again, this time for abstract a proton at the alpha position of the carbonyl group. The resulting enolate reacts with Comins reagent. Comins reagent is often used to introduce a triflate group in the molecule. Triflates act as oxygen-based alternative to halides, and metals can insert into the carbon-oxygen bond. The reaction begins with the enolate attacking the sulfur atom, followed by addition-elimination process in which the nitrogen atom along with its substituent leaves the molecule. In the next step, the two carbon units should be joined to this carbon atom. The best strategy to do this is the Suzuki coupling. The mechanism is slightly different from the Heck reaction which was described at the beginning of the video. Just like the Heck reaction, the first step is oxidative addition. The next step involves the contribution of the alkenyl boronate, which is called transmethylation. At this stage, the ligand is transformed from the organoborane to the palladium complex. After that, reductive elimination produces the desired product. In this reaction, 9-BBN adds regioselectively to the less substituted terminus of the alkene, and under palladium catalysis, the two carbon units adds to the molecule. In the next step, a triflate should be introduced into the molecule for a second time. To achieve this, the protected alcohol is deprotected by CSF. After the addition of the base, the triflate is introduced into the molecule using Comins reagent. The next step is enantioselective Heck reaction, in which the tetracyclic core of the final product is formed. Notice that there is a quaternary chiral center in the product of the Heck reaction, where this substituent has a specific orientation. In other words, one enantiomer is preferred over the other. The reason for this enantioselectivity is the use of chiral ligand called false ligand. During the reaction, palladium acetate exchanges its ligand with the bidentate chiral ligand. In this way, chirality is induced in the product. The first step is oxidative addition of palladium into the triflate. After that, the double bond coordinates to the palladium. In a migratory insertion step, the phenyl substituent is added to this carbon atom of a double bond to form a 5-membered ring in the middle of the molecule, followed by addition of palladium to the other terminus of the double bond. The final product is formed by reductive elimination. If you are wondering how chirality is induced, check out this video to take a deep dive into enantioselectivity. For constructing the core skeleton of our target, acid is added to the crude product in one pot to create the fourth ring. Let's move into 3D space to better understand the mechanism. Notice that there are two double bonds in this intermediate, but their reactivities are different. This double bond is activated by the nitrogen atom and gets protonated with the help of nitrogen's non-bonding electrons, resulting in the formation of iminium ion. Now the SH is set for the nitrogen atom to attack this iminium ion and complete the ring closure. Notice that the nucleophilic nitrogen atom is protected by the Bach group to control its reactivity. To simplify things, I represented this protecting group as a purple sphere. If you want to learn more about protecting groups and how they can affect organic reactions, check out this video. In the next step, The remaining double bond undergoes epoxidation. Notice the specific orientation of the epoxide ring. The reason for this orientation is the enantiomeric purity of the compound formed in the previous step. As a rule of thumb, whenever we have an enantiomerically pure compound, the followed reactions are also stereospecific because of the specific architecture of the molecule. After epoxidation with MCPBA, the bulk protecting group is cleaved under acidic conditions to produce a free secondary amine. Then it's again protected by allyloxycarbonyl group, which benefits from resistance to acidic conditions. Notice that both protecting groups are acid stable and are ready for further manipulation in the next steps. Now it's time to open the epoxide ring using alkyl phenylselenide, which is an excellent nucleophile. It easily opens the epoxide ring by selectively attacking this carbon atom. The reason is that the other carbon atom is more crowded and not accessible to the nucleophile. The resulting hydroxyselenide is not isolated but directly oxidized by an excess amount of hydrogen peroxide, forming an unstable selenoxide. This selenoxide abstracts a proton from its beta position, producing an alkene. Notice that there must be a syn beta hydrogen relative to the selenoxide for this reaction to happen. One key advantage of this method is that selenium is selectively oxidized in the presence of a hydroxyl group, which could be oxidized to a ketone. After forming the alkene, the hydroxyl group is deprotonated by imidazole and protected by acylyl ether. Now it's time to construct the last fuse ring in the system. First, this nitrogen atom is deprotected by palladium to produce a free secondary amine. Next, 2-iodo-2-butynyl tosylate is installed on the molecule by nucleophilic attack of the nitrogen atom. During this SN2 type reaction, tosylate acts as a good leaving group. After that, the sex-membered ring is formed by a Heck reaction. The first step is oxidative addition, in which palladium is inserted into the carbon iodide bond. During migratory insertion step, the 4-carbon atom unit is attached to one terminus of the double bond to create the sex-membered ring. Notice that the mechanism for removing palladium from the molecule is different from the standard Heck reaction. During the elimination step, the beta hydrogen atom and palladium must be seen to allow formation of a double bond. In other words, they need to be on the same plane. But in this structure, the beta hydrogen and palladium are trans to each other, and due to the rigidity of the structure, it's not possible for them to adopt a syn conformation. So, sodium formate is added to the system to remove palladium from the molecule. In this approach, a hydrogen atom is transformed from the sodium formate to the carbon atom bearing palladium. In addition, the production of CO2 provides a strong driving force for this reaction. In the next step, the silyl protecting group is deprotected by tetrabutyl ammonium fluoride, which is a source of fluoride ion. The resulting secondary alcohol is oxidized using Des-Martin protocol. Then, the corresponding enolate is formed by LiHMDS. After that, the ester moiety is introduced by methyl cyanoformate. Notice that the product exists in the enol form. The use of methyl cyanoformate allows for selective C-acylation to give the beta ketoester. This reaction proceeds via an aldol type intermediate which collapses upon workup to furnish the product. The next step is selective reduction. Notice that there are two sensitive groups, but only the ketone is reduced by NaBH4 in the presence of the ester. Subsequent reaction of the secondary alcohol with benzoyl triflate provides a good leaving group in the beta position of the ester moiety. Elimination under basic conditions provides the alpha-beta unsaturated ester. Now the ester should be reduced to alcohol, but it's conjugated with a double bond, so a more powerful reducing reagent than NaBH4 is needed to do this. So lithium aluminum hydride was chosen to reduce the ester. Finally, our target is produced by deprotection of the nitrogen atom.